Hello, my name is Aina Najwa binti Morni. My matrix number is CD240149. Today, I will guide you through the concept of steady flow device, commonly referred to as SFD, and explore their significance in industrial and daily applications. Steady flow devices are systems designed to maintain constant properties like pressure, temperature, and velocity during operation. These systems are engineered to deliver consistent performance over time, making them invaluable in industries where stability and predictability are critical. Examples of such devices include turbines, compressors, heat exchangers, and pumps. Among these, pumps hold particular importance, especially centrifugal pumps, which are the backbone of many fluid transport systems. These pumps are critical in applications ranging from municipal water supply to industrial processes and agricultural irrigations. Centrifugal pumps are essential because of their ability to maintain steady state operation, features that ensures their efficiency and reliability over long periods of operation. One of the primary features of pump is their ability to manage a consistent mass flow rate, ensuring that the fluid must move uniformly without interruption. This characteristic is crucial for systems that rely on predictable flow rates to operate effectively. Furthermore, pumps achieve this by converting mechanical energy into pressure energy. This conversion is typically powered by an external source, such as an electric motor or engine, which ensures the pump can deliver the energy required to sustain fluid flow. Centrifugal pumps play a pivotal role in water treatment and distribution systems. They efficiently transport fluids at required pressures, making them indispensable for providing clean water to households, industries, and agricultural fields. Their ability to operate under steady state conditions ensures that water is moved efficiently from raw intake point to the final distribution, catering to varying demands. This steady operation and efficiency underline why centrifugal pumps are cornerstone of modern water system and many others industry. Now that we have established the importance of steady flow device, let us delve deeper into pumps as a vital example of these systems. Pumps operate on thermodynamic principles that enable them to move fluids efficiently, regardless of the conditions they encounter. Their construction is a testament to engineering ingenuity. At the core of their operation is the impeller, a rotating component that transfers energy to the fluid by increasing its velocity. The volute casing, which surrounds the impeller, is designed to guide the fluid effectively toward the pump's outlet while minimizing energy loss. The drive shaft connects the impeller to the motor, ensuring a seamless transfer of mechanical energy into pressure energy. These components work in a harmony to ensure that pumps maintain a steady flow even under varying operation conditions. This reliability makes pumps indispensable in many sectors. For instance, in municipal water system, pumps enable clean water to travel over long distance and elevations, reaching homes and businesses. In agriculture, they are critical for irrigation systems, ensuring that crops receive the water they need to thrive. Meanwhile, in industrial settings, pumps transport fluids such as chemicals, oils, and slurries, supporting the production of goods and materials. The efficiency of pumps is another aspect that sets them apart. Their design and operation are geared toward minimizing energy losses while maximizing output. For example, the volute casing is engineered to reduce turbulence with the pump, conserving energy and maintaining consistent performance. The steady flow of fluid ensures that the system operates without surge or interruptions which could otherwise compromise efficiency. Additionally, careful material selection and robust design minimize wear and tear, reducing the need for frequent maintenance and ensuring long-term reliability. The role of pumps extends beyond mere functionality. There are critical links in ensuring the sustainability of many essential systems. Their ability to operate efficiently, adapt to different demands, and provide consistent results underpin their importance in modern infrastructure and industry. Pumps, as an example steady flow device, demonstrate how thermodynamic principles can be applied to solve real-world challenges, highlighting the intersection of science, engineering, and everyday life.
Hello, my name is Vanessa Ludak Nak Sampai. My matrix number is CD240119. In this presentation, I will discuss about the 10 characteristics of pump and the thermodynamic principles. Now, let's take a closer to look at the key characteristic of pump when operating under steady flow condition. Each of these points is essential to understanding how pumps behave and how we can analyze them using thermodynamics principles. First, a pump typically operates under steady state condition. This means that all flow properties like pressure, temperature, velocity, and mass flow rate stay constant at any fixed point over time. It's like turning on a tap and seeing the water come out smoothly without fluctuating. Second, we assume the mass flow rate is constant. That means the amount of fluid entering the pump per unit time is the same as the amount ejecting. This balance is important for accurate energy and performance calculations. Third, we define clear boundaries around the pump, specifically the inlet and outlet. These boundaries allow us to apply energy and mass balance equation effectively within a controlled volume. Next, pump add mechanical energy to the fluid. This is usually done using motor or engines. That energy increases the fluid's pressure, velocity, or elevation, making the fluid easier to move through a system. Fifth, in steady flow, there is no accumulation of fluids inside the pump. Fluid moves through continuously like a moving train that never stops, which helps maintain predictable behavior. This steady and consistent behavior means we can use the thermodynamics and fluid mechanics equation to predict and model pump performance. That is especially useful in engineering design. Of course, real pumps are not perfectly efficient. Some energy is lost to heat or friction. We analyze how much of the input work actually turns into useful energy. This gives us a way to evaluate and compare pump efficiency. These steady flow characteristics are not just theory. They are applied in real-world systems. Pumps are widely used in industry like a water treatment, agriculture, chemical plants, and even in our homes. Since the system properties does not change over time, it is easier to control and analyze. We don't have to deal with unexpected surges or drop in pressure or flow rate. And finally, all these characteristics allow us to apply the steady flow energy equation or SFEE. This equation is crucial in pump design and performance analysis, helping engineers determine how much work is done on the fluid. So in summary, these 10 characteristics describe the ideal behavior of pump under steady flow. Understanding this is the key to analyzing pump system thermodynamically and ensuring their performance efficiently in real-world applications. So this is the first law of thermodynamics, energy conservation. This equation is derived from the steady flow energy equation, SFEE. In pumps, shaft work is done on the fluid, increasing its enthalpy. The increase in enthalpy represents an increase in pressure or temperature of the fluid. In a pump, energy is added to the fluid to move it against the pressure. Second is second law of thermodynamics, entropy consideration, which entropy increases and limiting efficiency. This shows no real pump is perfectly efficient. Some energy is always lost due to friction, heat, or turbulence. The second law reminds us that perfect energy conversion is impossible. Hence, we calculate isotropic efficiency to evaluate performance. Entropy is increased also indicates irreversibilities in the pump system. Next is the application to pump, which is mechanical work increases, fluid pressure. The pump adds mechanical work to the fluid through the shaft. This increases the fluid pressure and sometimes velocity or height. For steady flow assumption, the mass flow rate always stays constant and energy is transferred continuously. In steady state, all energy inputs, which shaft work, go into changing the fluid's energy, mainly pressure head. So, this is the first law of thermodynamics, energy conservation. This equation is derived from the steady flow energy equation, SFEE. In pumps, shaft work is done on the fluid, increasing its enthalpy. The increase in enthalpy represents an increase in pressure or temperature of the fluid. In a pump, energy is added to the fluid to move it against the pressure. Second is second law of thermodynamics, entropy consideration, which entropy increases and limiting efficiency. This shows no real pump is perfectly efficient. Some energy is always lost due to friction, heat, or turbulence. The second law reminds us that perfect energy conversion is impossible. Hence, we calculate isotropic efficiency to evaluate performance. Entropy is increased also indicates irreversibilities in the pump system. Next is the application to pump, which is mechanical work increases, fluid pressure. The pump adds mechanical work to the fluid through the shaft. This increases the fluid pressure and sometimes velocity or height. For steady flow assumption, the mass flow rate always stays constant and energy is transferred continuously. In steady state, all energy inputs, which shaft work, go into changing the fluid's energy, mainly pressure head.
Assalamu alaikum. My name is Tawassul Muhammad. BD20703 is my metric number. So I'm going to continue with the component of our pump, which is there is a lot of components as we see in the slide, but what we are interested in basically our main three components, the impeller, the casing, and the motor. Our first component converts the energy to the flow motion, which is a really important procedure that we have to do so that the casing can direct the flow and increase the pressure, which is our which is our scoop. That's what we want. We want to increase the pressure, so that the casing will do this. Secondly, the motor will supply the mechanical energy, which is a very important process. About the design consideration for the pump, there is a lot of things we have to take consideration to, but again, most importantly is the material, the efficiency, and the corrosion resistance. So what do we mean by this? We mean that when we are going to select any material so that we can use in the process of design or manufacturing, we have to take in consideration that it should be a corrosion resistant material and it has a high amount of efficiency. So continuing with the case study that we are interested in, which is the water treatment plant, the scintigraphical pump in municipal water treatment. As we see in our slide, there is a graph and it showed a relationship between the efficiency and the flow rate, and our flow rate was about 500 meters per hour against the motor in kilowatt, which is 75, and the graph is showing a downward graph relationship that annual maximum discharge may go from the higher record until the less efficiency record, so that we can basically analyze this graph and
to go to our goal, which is to analyze the performance under the variation condition. So that's all for the case study. Continue with other friends' explanations and aspects. Thanks you all.
Assalamualaikum warahmatullahi wabarakatuh. My name is Waniel Fakri bin Muhammad Awad. So today I will explain to you about the simulation setup. For the simulation setup, there are a couple of software that we use. That was Python, JupyterLab, NumPy, and Matplotlib. So that was the software that we used to create our simulation setup. There are a couple of parameters that are tested in this simulation. That was flow rate, that is 400 to 600 meter cube per hour. Another one is height, that was 40 to 60 meter. And this one was motor efficiency, that was 85 to 95%. There are two types of equation that are used in the simulation, that was hydraulic power and input power. So I also put some of the reference picture in the slide that you can see. That is the simulation that we test. Okay, so get back with me with the simulation from the other slide. We just discussed about the simulation setup, and now we are discussing about simulation result. Using the software that I explained to you before, these are the results and the graph that we get from the simulation. The graph showed hydraulic power versus flow rate. We can see that the graph are going upward, showing the positive result that we get. So the hydraulic power output that we get from 400 meter cube per hour in 50 meter is for 45.15 kilowatt, and the other one that is 600 meter cube per hour in 50 meter. We get the result is 81.75 kilowatt. The efficiency for the 400 meter cube per hour is in around 84%, and the other one that is 600 meter cube per hour is around 80%. So we can conclude that higher flow or head increase the power but reduce the efficiency. That is what we can conclude from the graph and from the result in this simulation. That's all.
Salam sejahtera, sir. My name is Zakaria Austin and my number matrix is CD2400166. Today I will discuss about 4.0 discussion of result. Now I will present the discussion of our simulation result and how they relate to the performance of centrifugal pump. Let's begin with the effect of flow rate on power and efficiency. From our simulation, we observe the increase the flow rate lead to higher hydraulic power output. For example, at a head of 50 meter, a flow rate of 400 cubic meter per hour produces about 54.50 kilowatt. At 600 cubic meter per hour, the output increased 81.75 kilowatt. This is expected because hydraulic power is directly proportional to flow rate. However, we also notice that as the flow rate increases beyond the pump best efficiency point of BEP, the system efficiently drops. So even though more water is being moved, it's done less efficiently, which can cause long-term damage to the pump due to the turbulence or cavitation. In short, more flow equals more power, but not always best efficiently. Next, let's look at the effect of head on power consumption. At a constant flow rate of 500 meter per cube, a head of 40 meter requires about 54.50 kilowatt. Increase to the head to 60 meter rise the power demand to 82.75 kilowatt. This shows that higher head Volume require more energy because the pump must work harder to lift the water of overcome pressure loss in the system. This is especially important in high-rise building or long-distance pipeline. Now let's discuss motor efficiently. We simulate two motor efficiently, 85% and 95% at the same flow and head. The 85 efficient motor require about 80.1 kilowatt of input power. The 95 motor only need 71.7 kilowatt. So by improving more efficiently by just 10%, we save a significant amount of energy. This is important in systems that operate continuously like water treatment plants. Now on the flow head efficiency relationship. Our graph shows a linear increase in hydraulic power with flow rate at fixed about the system is efficiently insensitive operating to power from the pump BEP. Whatever flow is too high or too low, reduce efficiently and system stability. Conclusion here, always size your pump correctly. Oversizing on or undersizing cause inefficiencies and could reduce equipment lifespan. Finally, let's discuss real-world application. Modern systems can use smart tools like variable frequency drive to automatically adjust flow and head based on demand. This helps keep the pump with its optimal range and save energy. As a student and future engineer, this project shows us how practically simulation tools like Python and Jupyter Lab can be used to model real system. It helps us connect what we learn in theory, like the steady flow energy equation, to actual engineering application. Now let's move on the final part of our presentation, the conclusion. 5.1 Summary of key findings and insight. In this project, our group focused on analyzing a centrifugal pump as a steady flow device that we call SFDD using thermodynamic principle, especially the first law of thermodynamic. We applied this concept through a Python simulation using a Jupyter Lab, which helped us observe how flow rate, head, and motor efficiently affect pump performance. From our result, we found that higher flow rate and head lead greater hydraulic power, but they also demand more energy may reduce efficiently in operate beyond the best efficiency point. Motor efficiency play as a crucial role. Even a small increase can significantly reduce energy consumption. So this project didn't just help us to learn equation, it's that it helped us apply them to real engineering problem. Implication 5.2, that is implication of the study of for SFD. What does this mean for study flow device in general? It shows that design efficiently system depend on understanding how energy flow through them in pump and other SFD like turbine or compressor. We must consider the balance between power efficiently and operating condition. By applying thermodynamic knowledge, engineer can optimize system for performance, engineer saving, and sustainability, whether in industrial, architecture, or municipal setting. So this study gave us that number is just gave us insight into real world decision making as a future engineer. Feature 5.3 Future research direction in the field of SFD. Looking ahead, there are exciting directions for further research in this field. For example, using advanced materials that are more resistant to heat corrosion or wear, developing energy efficiently design like a variable speed impeller or compact pump system, integrating smart monitoring system using sensor and AI for real-time control, predictive maintenance, powering pump with renewable energy like solar, wind, especially in remote area, and running fluid dynamic simulation to reduce loss and improve flow performance. By exploring this area, we can design better, cleaner, and smarter fluid system, which is crucial for the future of engineering. So they're all from us. Thank you, sir.